Hi everyone, welcome back to Production ML Papers to Know. In this series, we'll give you an overview of some of the most important papers to know if you're building machine learning powered products, from the classic to the new and interesting. This week, we're going to cover a paper that makes progress on a problem that, if you've ever deployed large language models or other large models into production before, I'm sure has caused you a lot of problems. So let's dive in. Let's say that you deployed your large model into production and it's starting to interact with users. You explored it a little bit offline and it seems to be working well. So you're thinking, this is great. My product is going to change the world. Until your users actually start interacting with your model and they discover all of the kind of weird ways and edge cases that can fail that are sort of common in machine learning systems today. And if you're lucky, this is just, maybe a gap in the model's knowledge, like not knowing who the current president of the US is. But if you're unlucky, this could be something much worse, like the model saying something offensive. So as impressed as your users are with your demo, when they start interacting with your product, they're thinking, WTF, why did the model say this thing that's totally wrong? The question that this paper deals with is how to fix these WTFs. Now, if this were a regular software application, what we do is we just apply a patch to our software to fix the bug that we saw. But unfortunately, in machine learning, it's not so easy. The naive thing that we might consider is just retraining the model on this new data point, just fine-tuning the model. But the problem with that is it's really hard to avoid overfitting to that data point and correcting the problem for that data point, but damaging your model everywhere else. The normal way that you might deal with overfitting is to keep around the original data so you can retrain on some of the original data as well. But unfortunately, that means you have to hold on to that original data and you have to keep training on it, which can be expensive. Another approach that has been considered in the literature is meta-learning. But this is sort of still, I would say, an active research area and tends to be very expensive. So this isn't a great option either. Instead, the option that the authors consider in this paper is called model editing. The goal of this paper is to build a model editor. What's a model editor? Let's say that we have an input and a desired correction to the prediction that the model makes for that input. What a model editor tries to do is change the model so that it predicts the correct input while also changing predictions on related inputs that might need the same adjustment, but not changing behavior on unrelated inputs. And it's also important that this doesn't require access to the raw training data itself. So how do you actually build such a thing? The key idea is to take the gradient that you get from just normal model training, normal gradient descent, and transform that gradient before applying it back to the model. Double clicking on that. Normally, the way that we train a neural network is we do gradient descent. And what that means is we take a gradient step that updates the weights of each layer of our neural network so that they're better suited for solving the task that we want to solve. The key question we should be asking is, how can we actually train a model to do that, to edit gradients of our backpropagation process? And it turns out it's not as complicated as it sounds. First, we'll just train our base model just like we normally would to solve our task. Then we'll build a data set. And that data set will consist of three different things. First, edit pairs. These are the data points that we want to correct and the corrected label that we want to apply to them. Second, equivalence pairs. These are data points that should change their label in the same way as the edit pair. So for example, if the edit pair contains an acronym, then the equivalence pair could be the same sentence with that acronym expanded. So that should change its meaning in the same way as the edit pair that it corresponds to. And then finally, locality pairs. These are data points that should not change at all in response to the edit that we made. So these could be random data points that have nothing at all to do with the data point that we changed. Then we'll pass each of these edit pairs through our neural network, and we'll do a backward pass to compute the gradients of the loss function for that edit pair applied to each of the layers of the neural network. So what is the weight update that we would do naively if we were going to train on this data point? And then finally, we will optimize the loss function on the other two pairs that we have selected, on the equivalence pairs and the locality pairs. Let's talk about the loss function that we'll use to train this edit network. It consists of two terms, and let's expand some notation here. These are just the original parameters of the model, and these are the parameters that we get after we pass the original parameters through our edit network. The first term of the loss function just says our edited network should respect equivalence pairs. It should be pretty good at predicting the label for the equivalence pairs as well. The second term in our loss function is a KL divergence that measures the distance between two distributions. The distribution produced when you pass the locality pairs through the unedited network and the edited network. So what this is doing is it's saying the edited model should not change the output produced for our locality pairs. That's a high-level overview of this method, but if you actually want to implement it, there's a number of other technical challenges you'll need to solve. The first is that this gradient matrix that you need to update is potentially huge, which would make training a neural network that has that as input and output dimension very challenging. The authors use two tricks to deal with this. you have to decompose that gradient update into a sum of rank 1 updates, which is just derived from backpropagation. And the second is you need to share parameters between these weight update networks. It also turns out that this seems to be pretty tricky to train in practice. So the authors have a number of other tricks having to do with the model architecture, weight initialization, things like that they use to make it work. And finally, probably the biggest challenge with this method is that selecting this data set to train the update network with is more of an art than a science. And it's kind of done in a bespoke way for each of the data sets that the authors work with. So it could potentially be very difficult to design a good training set for this method for your data set. The next question that we'll ask is, does this actually work? In short, it shows promise, but you'll probably need to try this out on your own data set to know for sure. The authors find that their method has better edit success than baselines like fine-tuning, while having relatively little impact on non-edited data. And it also works for very large models, which is promising. So would recommend checking out the results for this in the paper if you're interested in learning more. They're quite technical, so I didn't want to cover them here. The qualitative results are also pretty interesting. In bold, the authors show the edits that were encoded as part of this process. And the ones that are not bold are how the edits affected other data points. And so you'll see that for the most part, the model edits work pretty well at correcting the suggested issues, while not having too big a negative impact on other points in the data set. Although in example 3, there is one example where this actually fails and changes the result of something that it shouldn't change. So to wrap up, I'm just really excited about this paper because this addresses such an important problem in machine learning, which is that we all the time have issues with models where they fail in ways that are unexpected. And there isn't really a good way currently of dealing with that. So I think this is a really promising research direction, but I also think it's probably not quite ready for production. The pros of this are it fixes these WTF issues in a principled and efficient way, which is really great. But the cons are it appears tricky to make this work in practice, so it might take a lot of effort to actually getting it to work for your data set. It risks damaging the rest of your model, even if just a little bit. So you'll probably need to have very good testing infrastructure and measurement infrastructure to make sure that the edits you're making don't negatively affect other parts of your model. I think probably most importantly, the single most challenging part of making this paper work is it's highly dependent on being able to create a good edit data set. And it's not obvious to me that this is something that every team will be able to do or is even feasible to do for every data set that you might be working with. So I'm really looking forward to future work where hopefully the dependence on manually creating an edit data set is loosened. That's all for this week. Join us in the future for more exciting production ML papers to know.